Hello everyone, welcome back to the sessions on the advanced communication. This is the session 7 in the unit 1, that is microwave devices. In this particular unit, we are going to learn about the device magnetron. This shows the picture of the magnetron here. The contents which we are going to learn are magnetron, that is the constructional diagram, how the magnetron is constructed, working, application. All these we will going to cover in this particular session here. Now starting with the definition of the magnetron. What is magnetron? Magnetron is a high power oscillator usually in cylindrical shape here. Means magnetron is an oscillator here. It employs radial electric field and axial magnetic field anode structure with permanent cavities. That is, it is an high power oscillator, microwave oscillator circuit, which is in the cylindrical shape. If you observe here, it is in the cylindrical shape here. Already we have studied the devices like the two cavity klystron tube and the reflex klystron. All those are in the form of the tubes here, but it is in the cylindric shape here. Now, here the particular electric field as well as the magnetic fields are used for the purpose here. To amplify the signal, both electric and the magnetic field, that is the electric field and the axial magnetic field are used, and the particular anode is having the permanent cavities here. Now, if you observe the constructional diagram here, the center one represents the cathode. This is the cathode structure here, or the cathode block, which is surrounded by the anode block. This is the anode here. Now, if you observe here, the anode is having the cavities here, permanent cavities here, and we can take output from the any one of the cavity. We can take output from the any one of the cavity here, and the space between here from this cavity to this is here. This is called as the gaps here. This is called as the gaps here, and here this full space it is act as the interaction space here. This is the interaction space where the electrons and the particular field will interact and electrons will give out their energy to the field here. This is the constructional diagram. And here if you observe here, same way, this is the cathode block which is surrounded by the anode block here. This is the anode, and this is having the number of cavities. This is having the number of cavities here. This is the constructional diagram here. Now, the working principle, how we actually the magnetron, it will generate the oscillations. How the oscillations are generated here. Now, if you see the view of that particular diagram here, the magnetron, this is the cathode here, and this is the anode here. This is the anode, correct? This is the anode, and this is the cathode here. The axial, that is the electric field, is also applied, and magnetic field is also applied here. Now consider only electric field, that is to the anode the positive voltage is given and to the cathode the negative voltage. Now first initially assume magnetic field is 0. To the anode the positive voltage and positive terminal, and to the cathode it is negative. And when this cathode block is heated, what will happen? The electrons will be generated here. When the cathode block is heated, the electrons will be generated, and as soon as the electrons will be generated, they will move towards the anode because they are attracted towards this positive voltage, and immediately they will reach the anode block here. As indicated by the path of the electron X. This is the path of the electron X. As soon as they are generated, they are reaching the anode block here. But now consider when the magnetic field is applied. The effect of the magnetic field is such that it will make the path of the electrons to bend. It will bend the path of the electron. Now some small amount of magnetic field is applied here, means what will happen? The electron Y, if you observe here, the path of the electron Y is bending here. The path of the electron Y is bending. Now increase the magnetic field strength still higher. This is the 0 magnetic field. This is one value magnetic field, and here it one more value here. So suppose we can say that here it is magnetic field is equal to 0. Magnetic field is 0 here, correct? And here in the Y magnetic field is having some value here, that is M1 value. Now increase this M1 to some more higher value. For example, M2. Magnetic field strength is M2, where M2 is greater than M1. Means we are taking some higher value, and M1 is greater than M here. M here, this one it is M here. Therefore, almost it is 0 only. The path is straight here. The electron path is straight here. But if you consider here, this is the straight path here where X is reaching. But if you apply some magnetic field strength, that is M1, what is happening? The path of the electron Y, it is slightly bending here. It is slightly bending here. Now you take one more, apply the still higher magnetic field. What is happening? The path of the electron beam, which is still bending here, and it is just touching the anode, and again it is returning back. It is coming back to the cathode here. If you observe here, it is just touching, and it is returning back from here to here. This field strength is called as the cutoff magnetic field. That is, this M2 is called as the cutoff magnetic field. Why? Because the electron beam or the electrons are in this particular magnetic field strength. Electrons are bending in such a way that they are traveling and they are reaching the anode block, and thus they are touching and they are returning back. That particular field strength is called as the cutoff. And if you apply the above cutoff, means they can't reach also here. They can't reach also here. Only they are taking the curve here. Here only they are taking the curve. But for the proper oscillations to generate, usually they will take this up to cutoff magnetic field strength here. Cutoff magnetic field strength. And one more thing is, that is, as we know, when the electrons are retarded, they are spending more and more time in the field here, the interaction space, if the electrons are retarded. But if the electrons are accelerated, they will very fastly they will reach the anode here. But if they are retarded, means they are spending more and more time here in the field. Therefore, what will happen as they are spending more and more time in the field here, like this, they are giving their energy to the field. And also the bunching process also takes place here. Number of electrons are bunched together, and they are giving their energy to the field here. Therefore, this is achieved in the magnetron. Initially, we have to assume that a small noise field or the field will be there. Correct? Field will be there. And when the particular electrons or the magnetic field is applied in a such a way that they are bending like this instead of going directly, and when they are taking the longer route to return back, what is happening? They are spending more and more time here, because they are spending longer route to return back here. Now what will happen when they are taking the longer route, means from here to here, like this, they are taking the longer route. Therefore, bunching of the electron also takes place, and also the particular here to electrons are bunching here, and also they are spending more and more time, and they are giving out their energy to the field here. Therefore, whatever the field we have is the noise field is there, the small, after some time what will happen at the output cavity, if you take any one of the cavity, the strength of the signal will be of high strength here. The strength of the signal will be high strength here. Therefore, this is the basic principle of the working of the magnetron. That is, here the electric field is applied between cathode and the anode block, and the particular magnetic field is also applied so that the bending of the electron beams will takes place, and the bunching takes place, and the more and more they are spending in the interaction space, and they give out their energy to the field there, and therefore the field will increases. The field will increase. This is the working here. Now, one of the limitations of that particular magnetron is what will happen, that is, here the number of cavities are present here. Suppose this particular magnetron is designed for one particular mode or one particular frequency. For that, we are applying some voltages here and some magnetic field strength. But due to some fluctuations or some small variations, there may be chances that the magnetron may jump from one mode to other mode. The output frequency may change there, or it may vary. that is called as the mode jumping here. To avoid that one, the alternative cavities are here. The alternative cavities are connected here. Alternative cavities are connected such that suppose this is cavity 1 here. This is also alternative. This is 1. It is marked as 1 here. Now this is 2. This is also 2. And this is also 2. Like this. These alternative cavities are connected here using one high gauge cable here. These are connected here. This one means here this should be connected to here. Correct? Like this. These are connected to avoid that mode jumping here. Now that is called as the strapping here. You can observe here the particular alternative, the dot indicates the connection here. The dot indicates the connection and these are the strapping rings here. High gauge wires are used. Alternative blocks are connected such that during the particular some variations also there is no mode jumping. Whatever the frequency is designed, on that only it should operate here. Here you can see the two cables here. This is one and this is the outer one. Those are connected the alternative cavities here. Now this is also having one of the limitation, that is whenever the particular this one is connected here, we are using the high gauge wires, means there may be the loss of energy in the form of the heat dissipation in these wires. Therefore, to overcome with this problem, one more solution is the rising sun, that is rising sun magnetron. Rising sun magnetron means what? Instead of connecting the alternate cavities here, the shape is made unique here. Alternate, that is this cavity are same shape, and this alternate cavities are of same shape here, such that the mode jumping is avoided. This is called as the rising sun magnetron here. Now the performance of the magnetron, that is power 10 kilowatt to 5 megawatt depending on the application. Frequency range UHF band up to 100 gigahertz. And the frequency range is UHF band up to 100 gigahertz. Efficiency is 50%. And the duty cycle usually you will get up to 0.1% here. Applications, that is usually these magnetron oscillators are used in the microwave ovens, in the pulsed radar system, and also in the linear particle accelerators here. These are some of the applications of the magnetron. Now just we'll go through the one of the videos such that it will demonstrate how the construction of the magnetron here.
Hi, today we are going to uncover the secrets of the humble magnetron. One of the applications for a magnetron is something you already know about, a microwave. So what is a magnetron? Well, the short answer is it's a radiation emitter. No, wait. Before you go running to the hills, just remember that the radiation emitted by this is 2.4 gigahertz, which is relatively low, so you're not at risk of developing cancer or anything. However, it is a kilowatt, which means it's very high powered, so it will burn you. But how does something produce a kilowatt of 2.4 gigahertz electromagnetic radiation? Let's find out. Alright, so here's what the inside of a microwave looks like. Here we see the magnetron, which emits waves into the main cavity. That's this part over here. Oh, and it's cooled by this fan. Whee! Down here we have a 2000 volt transformer and a 2000 volt capacitor. And it's because of these that you never work on a microwave while it's plugged in. I've pulled out this microwave transformer as an example, and you can see how the high voltage arcs across the air, superheating it into a plasma. So here's how a magnetron works in theory. We already know that it needs high voltage in order to operate. This is so that the electrons can jump off the cathode and move freely around the chamber. Every magnetron has two powerful permanent magnets inside of it. They're there to create a constant magnetic field pointing through the cavity of the magnetron. Now here's where the physics gets a little weird. We need to remember a thing called the right hand rule. You hold your fingers in this pose. Your middle finger points in the direction of the magnetic field. Your index finger points in the direction of the current, or the velocity of a single moving charge, and your thumb points in the direction of the force that charge will feel. Now that we've discussed the right hand rule, let's take a look back inside of a magnetron. As we kind of touched on earlier, we know that the electrons are emitted out radially from the center cathode, and there's also a magnetic field going right down the middle of the magnetron cavity. So how does this interact with the electrons? Well, using the right hand rule, if we know that an electron is heading straight out from the center, then the magnetic field is going into the plane of your computer screen, then we know that the force is going to be accelerating that particle this direction. And after a moment, the particle will have a new velocity like this, and so on and so on. Inevitably, what this electron is going to do is it's going to follow a spiral pattern going outward. What we've just described is what physics knows as a cyclotron, when you can get charged particles like electrons to cycle around in a spiral pattern. When these spiraling electrons finally make their way to the anode block, the outside wall of the magnetron cavity, they will induce a charge separation, a voltage across the anode resonating cavities. Those are the smaller circles on the periphery that we see. Why the electrons do this is a lengthy explanation and out of the scope of this video, so I'll leave some links in the description for your own study if you're interested. Now let's take a closer look at one of these resonating cavities. Well, we see that across this resonating cavity, the base of it, where the charge separation is, kinda looks like a capacitor, and that loop going around the circle kinda looks like an inductor with one turn. Well, let's model it as such and see what happens. This capacitor portion at the bottom creates a constant electric field across it thanks to the charge separation, and the one-turn inductor will create a magnetic field going in and out of the plane of that circle thanks to the rotating current around it. Essentially, it's a really weak electromagnet. So what we see is that the electric and magnetic fields are perpendicular to each other, and oh my gosh, it's electromagnetic radiation! As evident by the alternating electric and magnetic fields that are perpendicular to one another. We can solve for what the resonant frequency is by solving this equation. As we can see, both the inductance and the capacitance are in the denominator under the root, which means that the smaller they are, the higher frequency we're going to get. Since we know that we're talking about a magnetron from a microwave, we can expect this to be somewhere around 2.4 gigahertz. But wait a second. These waves aren't very powerful. In fact, they're incredibly weak. So how does a magnetron make them more powerful? Well, let's take a look back inside the magnetron at the electric fields created by this charge separation once more. The red lines you see here are the electric fields created inside the main cavity of a magnetron, and the arrowhead points in the direction that these fields are going. Now let's consider an electron as it interacts with these fields. Well, it looks like the electron is occasionally going against the electric field, which will cause it to slow down and use energy. This is called retarding the electron. And as this happens, that energy needs to go somewhere. It's absorbed into the RF, the radio frequency that's being created by the resonating cavities. And this is how a magnetron takes that teeny tiny power of an electromagnetic wave and makes it very powerful. There is a lot more we could say about this. In fact, we could be here all day. But if you're interested in learning more, I'll include some links and references in the description for your own study, if you are interested. But for now, I think you get the idea, so I'm going to move on. In fact, let's take a look back at the magnetron I have sitting on the table and see what it looks like. Now this top piece here is the antenna for the magnetron. Now you may expect the waves to come straight out as if it was coming out of a gun, but that's not actually what it looks like. I'll animate this as best I can, but the output from the antenna looks something like this. These shapes that you see here are the primary lobes. This is where you can expect the greatest intensity, which means something directly in front of the magnetron would have almost no interaction with it. Alright, now that we know what to expect, I think now we're ready to cut this thing up like a Christmas ham and see what it's really made of. Okay, this is very important. You see this pink band here? This is a ceramic insulator that is oftentimes made out of beryllium oxide, which is extremely dangerous. If it's broken and you get particulates either in your mouth or in your lungs, you could potentially develop a condition called berylliosis, which will have both acute and chronic side effects that'll probably end up killing you. Oh, and it's also carcinogenic. In fact, magnetrons are full of bad news, so I can't stress enough to wear some proper protection while you work. Okay, it's a little while later and I've made some progress. So I've removed some of the outer case of the magnetron. Let's see what some of these parts are. Oh, well, this one that just fell off. This is just a brass reflector. It prevents waves from bouncing back into the magnetron. It's not really important. So here beneath the antenna and beneath the cover, we can take a look at one of these permanent magnets. There are two of them, once again to make a magnetic field going through the cavity of the magnetron, which are these two coils here. Alright, let's see if I can get off one of these permanent magnets. So with everything else gone, I'm just left now with the resonant cavity of the magnetron. It's sort of unbelievable that beyond all the bells and whistles, a microwave oven can just be boiled down to this. I think I'll bisect. We see that the inside is made out of copper, which is not what I was expecting. I thought it would be made out of steel, which would be a much tougher material. This actually wasn't too bad to cut through. Here, that center rod right there, that's the filament where the electrons are ejected from. That's superheated, by the way, so that the electrons can migrate away from it into the cavity. Now, I depicted it in the schematic as circles, but in this magnetron, these triangular regions, trapezoidal regions, these are the resonant cavities for the electrons. Now, I know that they've been trying to make magnetrons a lot cheaper over the last decade or two. I never imagined they would simplify it down so much. The other one looks pretty much the same. Once again, we got that filament action going through there, and this leads up to the antenna.
Okay, students. Now that completes the topic on the magnetron here, and in the next class we'll go for the next session. Thank you for watching. Thank you.